With the goal of taking action to combat climate change, studies directed on the gradual shift to utilize greener energy are in demand, particularly on the electrification of traditional fuel-dependent systems. Given the status quo, efforts on electric conversion of marine vehicles have been made for large-scale projects. With the goal of electrification being inclusive for small-scale industry marine vehicles, this study focused on sizing and designing a fully electric propulsion system to serve as a viable alternative or a potential replacement for traditional fuel-powered fishing boats. Along are three major objectives. First, to create a model similar to the existing hull structure of fishing boats to be used for designing, simulating, and testing of the modified layout for electric boats. Second, to size, design, and test the fully electric system for rural fishing boats. And third, to analyze the capacity of the electric system and see if it is at par with the operations of traditional fuel-dependent fishing boats. In order to accomplish these objectives, this research was initiated with an on-site survey to get the dimensions and measurements of the boat, to map the route operations, to get the fuel consumption, to record the varying speed of the boat, and to generally observe the day-to-day operations of the rural fishing boat. Given the surveyed rural fishing boat in Anilao, Mabini, Batangas, a 3D model was created in order to simulate the projected resistances. These resistances aided in determining the powering requirement based on the vessel's speed. The faster the cruising speed, the higher the needed powering requirement. From the survey, considering the boat's average speed of 7 knots and mode of 8 knots, a 5 kilowatt AC motor was sized for the electrical system. It has a peak power of 13 kilowatts with 3,000 RPM as the rated engine speed and 6,500 RPM as the peak engine speed. Given its voltage rating of 72 volts, a battery bank with 23 battery cells was used. Each battery cell has a voltage rating of 3.3 volts and 60 Ah charge capacity. Upon emulations, the projected length of operation that the currently designed system can handle is 2 hours and 16 minutes. The use of the available 60 Ah batteries for the testing resulted to 66.5% completion of operation. In contrast, the use of the designed system with 100 Ah charge capacity of batteries would result to 100% completion of operation with 360 watt-hour spare energy. After testing the system performance, further step to this research is the electric propulsion prototyping, which is mainly focused on the structural and mechanical adjustments in order to fully integrate our design system to the existing hull structure of the rural fishing boat. This new layout integrated the shaft and propeller needed for the actual operations of the fishing boat. As a proof of concept, the prototyped electric retrofitting kit is applied to the fishing boat. As seen, it is at par with the speed of the usual fuel engine boats and has significantly reduced the engine noise. Moving forward, to meet global standards, we need innovation that connects technology with tradition. Hence, we introduced the Vessel Interface System. VIS is a smart platform designed for fishing boats that features a digital traceability logbook for real-time catch data and market transparency, a navigational policy map to ensure compliance with legal fishing zones, and a livelihood center for communication and safety alerts. Furthermore, by analyzing data trends, VIS can help us identify spatiotemporal patterns, leading to improved efficiency, better management, and stronger motivation within fishing communities.